today we'll talk about LED decomposition. Alright, so this is the first topic of chapter 10. Chapter 10 of our text. And in this, so what is LED decomposition? It's a method to solve a set of linear equations. Just like other methods we talked about in other classes. Gauss elimination, Cramer's rule, Gauss-Jordan, and Gauss-Seidel maybe. So we talked about the so this is just like another method in neural methods. So in this, so you may see this sort of question in the exam, sample question. Solve the following set of linear equations using LED decomposition. Right? So in that question, will be given a set of linear equations. Here we have a set of 3 equations and 3 variables. So we know the number of equations is equal to number of variables. 3 equations, 3 variables. If I happen to ask you or give you a set of 4 equations, there will be 4 variables. So this is the most simplest way to create a set of linear equations. And some of you probably really understand what are the values for the unknowns. Look at the equations. But in our exam, you'll never know. You have to really solve them in mathematical process that you have to follow. So we'll talk about that today. So this is a question that we have to solve. So, but before we get there, I need to really talk about how does this LED decomposition works. Alright? So let me raise it a little bit. So I need a duster anyway. So one thing we know, one thing is that we know for set of linear equations set A, which is Gaussian matrix, is really multiplied by variable matrix equal to what? Your C. A that will form from this setup, which is Gaussian matrix, variable matrix is multiplied by something that is equal to constants. So these are a special simple setup for matrices. And for LED decomposition, what you have, so here you really have to decompose matrix A into 2 different parts. Like say for A is really part L and U. L and U. So if this is the equation, and for this the equation, if I place the value of A into this equation, so we get like L into U into X equal to C. So we haven't done anything but we just placed the value of A, which is 2 matrices, lower matrix, upper matrix. The value of L and U went up here. So L and U is replacing A, and we're keeping the X intact, is equal to C. Alright? So that should make sense, right? So instead of AX equal to C, we can write LU X equal to C. Considering that if you multiply L into U, you will get A. And probably I should have shown you that before, but for now, just take it from me. So if we can somehow, some way, we can decompose a matrix in two different parts. If you multiply these two matrices, you will get the original matrix. So L and U is really product of, parts of A, or A is product of multiplication of L and U. You can say either way. Alright, so we just put L and U in place of A, we take say equal to C. Now, if you multiply for the process, you have to do certain things, as you know. So if you multiply both sides, like say multiplying both sides with L inverse. So inverse matrix is another thing that you have seen in your other math classes, and I believe we will have another chance to find inverse matrix in next class or so. So for now, what I'm saying that for any matrix, they are multiplied into inverse. Alright? So multiplying both sides with L inverse, you may get like say L, this L, multiplied by L inverse, then if U here, then X equal to C into what? L inverse. So for this same setup, if you multiply both sides with the same matrix, it doesn't change. It's same. Because you are multiplying both sides with the same value, same matrix. So we can do that, as you know. So if you did that, so probably you can get what? L inverse, you get identity matrix I. So usually if you multiply any matrix with the inverse, you get identity matrix. And we'll talk about this later, identity matrix. I know many of you already know. I need a glass of water. So you get I for this, then you get U, you get X equal to C into L inverse. Right? So again, if you multiply two matrices with I, you get same thing. I is nothing but 1 0 0 0 1 0 0 0 1 matrix. Because all the diagonal elements are 1 1 for 3 by 3. Alright? So identity matrix is just like that. I'm pretty sure all you know about this. So I multiply by U and X is equal to C into L inverse, and then if you multiply any two matrices along with I matrix, you get the same two matrices. These are rules. So we can say from here, we can say U into X equal to C into L inverse. Alright? So we can say UX equal to C into L inverse. Now, just to prove, just to solve the set, we have to consider some values, some matrices, for the sake of proof. Alright? So here, what they did in the text, of course, it's all out of the text. I didn't make things up. This is, when I was a student, I learned this process myself from our teachers, and I'm just showing the same thing to you. It's nothing made up. Alright, so what I'm saying, you can really consider, say, let C, this part, right hand side, let C into L inverse, C into L inverse equal to some sort of matrix Z. Alright? So we can say from here u and x equal to z. Make sense? So what we did, we just placed z, that means we consider for this part, just place the value of CL inverse to z here. Alright. So CL inverse, this part, let's consider that CL inverse equal to z. So we can say ux equal to z, right? So let us call this equation number 2 maybe. We only have one here. Now, if I can erase now, if I can take this one back here, so this part will follow from here. So we can say from here we can say C L inverse equal to Z. Just from this. Now we can write this into, like, say this is nothing but C matrix divided by L matrix equal to Z matrix, right? 1 over L, or we can say LZ, L matrix into Z matrix equal to C matrix. So we can call this equation number 3. So so we really found two different equations from equation 1. Equation 1 was what? Equation 1 was A into X equal to C, right? That was equation 1. So from this setup, so this is fact for any matrices. From this very fact, we just derived two different equations. Why? Because we need to follow these two different steps to solve for unknowns using decomposition. Alright? So you can see, just pay attention to these three equations. A is not here anymore. A is replaced by L and U. X is there, C is there, Z is the matrix that came up because we consider CL inverse equal to Z. Now you really have to do these two different steps. First, equation number 3. C has to be computed first. 1 matrix into Z matrix equal to C. From here, if I can get Z matrices, value of Z matrix, and if I somehow, some way, if I can get this Z matrix from here, from 3, if I place that value to equation number 2, we can find what? The value of unknowns. X matrix. Alright, with X matrix is nothing but X, Y, Z. So, if I had to ask you a question in your exam, say, how does decomposition work? So you can really, for that very question, you can convert, you can derive these two equations from here. That should be a good answer. And then you have probably write down that we have to solve the equation 3 first. From 3 we can get the matrix. We have to develop the matrix in equation 2. We can find the unknowns. Thanks. Alright. So this is the very first part of explaining how decomposition works. And in my next lecture, today we'll solve a set of linear equations using these two different steps.